Now, I assume a certain background from you, and it will help us in pacing the progress in this course if we can find out how much of background you have. Essentially, you would have done some data converters course perhaps earlier. So, how much of background do you have in understanding and implementing data converters? If you have none at all, that's fine. Meaning, I assume no background if it is not necessary, but if you have some background already, then we will go quicker over that portion. Now, so what is the problem in front of us? The real world standard statement, real world is analog, most of the treatment that we do is in digital. Therefore, almost anything which requires digital treatment will require an analog to digital conversion at the input side and a digital to analog conversion at the output side. Now, the requirements can be quite different of different systems. Speed requirements, resolution requirements, and the requirements of accuracy, etc., can be quite different. And then these are obviously also controlled by things like cost. So there are different architectures of conversions, analog to digital conversion, and we are going to study many of these and their implementation using generally CMOS in this module of lectures. Okay, so that is roughly the scope that we will cover in this. We begin first by data representation, because essentially if you are doing A to D conversion, then the analog quantity needed no representation. Here is a voltage or here is a current. However, if you want to convert it to digital, then you need to know how to interpret various bits of the digital form. Okay, and this interpretation happens to be somewhat different from what we are used to. Therefore, I make it a special point to introduce it in advance, because most of A to D literature, unfortunately, uses somewhat incompatible conventions for representing bits. Then we will first look at the common converter architectures, flash converters, successive approximation, charge balance, charge redistribution, etc., etc. And then eventually we will look at a class of converters which are called sigma delta converters. These are oversampled converters in which you sample the analog quantity more often than necessary and improve resolution as a result of this. So it's a speed versus resolution trade-off. So this is roughly what we intend to do in this module. So first let's look at data representation. First of all, this warning that I have given you, that it can be quite different from the usual digital data representation. For example, in digital circuits, if you have an n-bit quantity, typically you would go from 0 to n minus 1, A0, A1, An minus. So we are quite used to seeing, let's say, an 8-bit quantity saying D0, D7. And generally, D7 is the most significant bit, D0 is the least significant bit. The situation is exactly the opposite in A to D conversion literature. Be very careful about it when you read papers or whatever. It's quite common to see things go from 1 to n, and A1 or the lower index number is often the most significant. Okay, so the MSB is often, it's not universal, but often the most significant bit, and it often goes from 1 to n rather than going from 0 to n minus 1. Okay, so in much of the expressions that I use, I'll try to follow the data conversion conventions. I'm just pointing out right at the outset that it could be different from what you're used to. Okay, so don't just assume that the highest index bit is the most significant bit. So that is what I'm saying, that and bit 1 is often the most significant. Now, the standard D2A to D conversion, as soon as you convert from analog to digital, digital is a discrete system. Okay, you go suddenly from one count to the other. Analog is a continuous system. As soon as you convert, therefore there is a quantization. That means you must say that a range, a step size from this to this is all represented by one digital signal. Okay, smaller this range is, smaller is this error of representation. But essentially you have swept an entire step into one symbol. Okay, so essentially if you were to plot x itself versus x, then you would get something like that. But Now you have a stair-step approximation. Okay. There is also a slight change, if you are careful to note here, okay, in A to D and D to A conversion. So essentially what happens when we do D to A conversion, that I'll give you a digital word and you give me an analog quantity which is proportional to it. So if I give you 0, there are other conventions, but suppose if I give you 0, you would expect the analog output to be 0. And if I give you 1, the output should suddenly jump to 1, right, and so on. However, when you do A to D conversion, then you have to put thresholds, and you will say everything below this value is 0 and everything above this value is 1 till some limit, and then above that limit is 2, and then above that limit is 3. This part is clear? So I have to do thresholding, and these thresholds are not identical to the discontinuities in the D to A case. Okay? So it's quite clear. For example, suppose you want to go from 0 to 1, the threshold is at half. Right? You are saying that everything below half should be treated as 0. Everything above half should be treated as 1. Right? So while these two plots look quite similar, notice that they are displaced by half a bit. Okay? Normally, since you would like to have good resolution and each bit size is quite small, this should not make too much of a difference. But if you have a feedback system in which there is D to A and A to D in the same loop, then you should be aware of this offset. Okay, so there is a half bit offset between the steps of quantization in A to D as opposed to D to A. Okay, so D to A, digital word says 0, output is 0, but in A to D, 0 to half is the digital word 0, half to 1.5 in fact is 1, 1.5 to 2.5 is 2, so everything is shifted by half bits. Okay, this is the shift because the whole digital word spans an entire range. Okay, so this part is important. Sometimes when you have feedback, this could be even significant. Now, if I had a very large number of bits, then what will happen? This step size will become smaller and smaller. In the limiting case, if I had infinite bits, this would become just a diagonal straight line. Okay, in both cases. That means that half bit offset will also now become 0. Correct? So in both cases now, I will get the ideal case. So not only does the quantization disappear, the mismatch between A to D and D to A disappears as the number of bits becomes quite large, and I get just a plot of x versus x. Right? So that's the ideal case when you have infinite resolution. As you come down, you hope that the average slope will remain 1. Right? This offset is there in the A to D, D to A case of a half bit, but you expect that the average slope passing through this step, these steps, will still be 1 because after all it is the same quantity which is being represented either as an analog or digital. Right? So therefore you expect that the line passing through the origin with a 45-degree slope is what you would have liked ideally. Therefore all non-idealities should be measured with respect to the straight line. Okay, what non-idealities are we talking about? Yeah, for example, quantization error, the very first thing. Okay, so if you are talking about quantization error, because of this very nature, the number or the value is not quite what that ideal straight line would have had. So when you say this is the quantization error of this D to A, then you will see how far is the output analog from that ideal straight line. Correct? Similarly, when you convert, you would say that on this straight line, I would have got this point. Instead of that, I got this point. Okay? So that is the quantization error. So when all the errors in A to D, D to A are specified, they are essentially, this straight line doesn't exist. You don't have an infinite accuracy A to D. So it's a fictional imagined straight line, but it's the ideal straight line passing through the origin with a 45-degree slope, and all for example, gain error. That means the angle is not quite 45 degrees. The gain is not quite 1. in that case it will be measured, the angle will be measured with respect to this 45-degree straight line. Similarly, quantization errors, similarly nonlinearities, etc. So whenever you measure these things, they will be measured with respect to that ideal characteristic which represents an infinite resolution A to D or D to A converter. Now the data needs to be interpreted. You have a combination of bits and this data. Now you have to make sense of it. Making sense of the voltage was given voltage, current was given current, there was no problem. Now you convert it to a digital, then you have a collection of bits and these bits must now be interpreted. There are various conventions which are in use and therefore the value will make sense only if you also understand this convention. Okay, otherwise the digital word makes no sense. For example, for unipolar quantities which can't have a sign, which are always guaranteed to be positive, it's very common to have the standard binary representation for it. Okay, notice that when n equal to 1, the range of this is from 1 to n, as we had said before. An is the nth bit, and when a is 1, this is the most significant bit because its place value is half the total range. Okay, because n by 2 to the power 1. So therefore the most significant bit is bit 1, the least significant bit is bit n, which has a step size of an divided by 2 to the power n. Okay, so an is this, it's the digital bit, could be 1 or 0, and what we are saying is that I am going to, in case of D to A for example, my output voltage will be this expression, right? The place value of each bit will vary in a geometric progression and the most highest place value will be for bit number 1. Okay, so this is of course straight. This is how we interpret most of the digital words. There is not too much to write home about this. However, suppose the number can have positive as well as negative signs. So what can I do? Okay, if the number could be positive as well as negative, then one obvious way is that I can shift the entire range so that the shifted range becomes positive. Right? So suppose I have some value which goes from minus VFS, V full scale, Fs is full scale, right? So suppose I have a value which goes from minus VFS to plus VFS. First of all, notice that the entire range that I have covered has become double. Okay, forget about the sign. The entire range has become double. Because I am covering doubling the range with the same number of bits, then each bit will have twice the size. Right? So my resolution, everything is coarser compared to that because simply I am converting a larger range. Right? In addition to that, what I could do is that, alright, I will now represent from 0 to 2 VFS using the old convention that I am familiar with it and assume that a VFS is to be subtracted from it. Right? This is called offset binary because it is essentially the same convention as we had in binary, except that I have offset it by the magnitude of the maximum value, which is half the range actually. Right? So I express it as if it is binary and subtract VFS from it. Right? So whereas the expressed binary number will go effectively from 0 to 2 VFS, the actually interpreted range will now go from minus VFS to plus VFS. This is how I can handle the binary values by the signed value. The other this thing is a ones complement representation, not very widely used, but it's still in terms of implementation sometimes it can be easy. So what I am saying is that the output, by the way, this diagram probably is not accurate, but just try to understand. So just right now qualitative. I'll have to make sure that it is accurate. So what we say is that from 0 to plus VFS, I have a bipolar signal, and from 0 to VFS there is no problem. It's positive. Okay, so I use the same as usual, and have a 0 in front of it. Okay. However, if the number is negative, then all bits are complemented. Okay. So this is called ones complement, and notice that when all bits are complemented, essentially the value has a jump. Okay, this you've seen in 2's complement. When 2's complement, you just add 1 to this. Okay, so you are quite familiar with the convention for interpreting signed numbers. It is the same thing applied from A to D, and you just added 1. You just take that number and add 1 to it. There is also sign magnitude, in which you reserve 1 bit for magnitude and the rest is now positive, right? 1 bit for the sign and the rest is now magnitude, therefore positive, and you interpret it as if it is an n-1 unsigned number. Okay, so notice that as the sign bit flips, that means as you go from 011 to 100 in this example, the value is 0, the sign becomes negative, and there are 2 representations for 0. Okay, 000 as well as 100 represents 0. Okay, so 2 symbols are used up now for representing 0, plus 0 and minus 0. Okay, the magnitude being 0, sign being either 0 or 1. Okay, and then of course the magnitude has this, the higher the magnitude, this is how it goes, right, except that it is going in the opposite direction, therefore there is a jump of half the range here as the number increases. Notice that there was a jump of the full range as you go from here. That means as you go from let us say 0111 to 1000, right, you have gone from most positive to most negative in one step. So the jump involved is twice the maximum magnitude, the full range. Okay. In addition to that, there are 2 other codes which are important. There is gray code. So gray code essentially this is the code that you use in Kano maths and so on, which ensures that only 1 bit changes at a time. So this has advantages. This has advantages beyond that of digital power. Of course, there is advantage in switching. Suppose something is counting up or down, then only 1 bit changes at a time. Therefore, only 1 line needs to be charged and discharged at a given time. So this has certain advantages if you know that numbers are not going to change randomly, but in a regular manner. Okay, but it also has certain other advantages in the analog domain, because only 1 bit changes at a time. You don't have to worry about certain glitches which will come if 2 bits are changing at the same time. Okay, so notice that you have some number, you are going to some other number. Each number has a corresponding weight, corresponding place value. Now if both bits are changing in opposite directions, it is possible, depending on the size and the time of these, that you can produce in between some glitches which is not the proper value. Okay, if more than 1 bit changes at the same time, some bits going up, some bits going down, and their place values being different. So while 1 bit has already settled, the other has not, you will go to some in between arbitrary value. It can produce glitches. Okay, on the other hand, gray code will have this advantage that as you go from as long as the numbers are changing regularly, only 1 bit will change at a time. But this advantage will be lost if the number is changing randomly. Okay, then you have the same problem. But if, for example, you have a ramp or you are sweeping something and so on, then the gray code can be advantageous because then it will avoid glitches. Okay, so that is one area in which you use gray code. An important code is the thermometer code. It's not a very efficient code in the sense that it uses a large number of bits, but it is essentially as the number increases, you keep on adding more and more ones. So essentially the number of ones is proportional to the value. It's not a binary coded value. It's like the thermometer in which the mercury moves. Okay, and as the temperature increases, the mercury moves linearly. So essentially the 1 moves up as the value increases linearly. So for every increase, the number of bits is not logarithmic because there is no place value, but you need n bits for representing n steps, whereas you require n to the base 2 log if you have a binary representation. So this is not a binary representation as yet. It requires large number of bits. On the other hand, for fast systems, it can be quite advantageous, and you often need then converters from this thermometer code to binary. Okay, these are the common codes which are used in both A to D and D2A, and we can immediately see an application of this in what is called a flash converter. Okay, I am going to, by the way, jump between A to D and D to A, because very often very similar techniques are going to be used, and I'll tell you whether I'm talking A to D and D to A. I'll also ask you to think what will happen if I had to make the corresponding version of D to A using this trick. But this one is an A to D converter. What I have is a reference voltage here, and I divide it equally into equal steps. Okay, so this will then provide those thresholds, and remember that now that half bit offset will be accounted for by a value of R, which is not identical to the rest, right? So this value, rather than being taken from 0, is being taken from R by 2, half bit, okay, and then 3R by 2 and 5R by 2. Okay, so you have these thresholds, and the input is fed in parallel to all the comparators. Okay, now right now I'm assuming ideal comparators. We will just do a little bit of evaluation of what happens if these comparators are not ideal. But right now, just to understand, let's say that these comparators are ideal. In that case, there is no offset, and assume that these ref values are all equally spaced and at the proper decision values that we had talked about earlier. Then as the value increases, initially, suppose the value is very low, notice that the input value is fed in parallel to all the comparators. Okay, so the advantage of this system is that all the bits are determined at the same time in parallel. Okay, this is one of the few systems which is capable of doing this. Therefore, it's one of the fastest ways of converting analog to digital values. So all the comparisons are occurring in parallel, and they do not depend on the result of comparison of the previous value of some more significant, less significant bit. So in short, drawing a parallel from arithmetic circuits, there is no rippling of carry or rippling effect in which something must be completed before the next bit can even be attempted. Okay, so that makes the system basically sequential. This system is basically parallel. Of course, then you can clearly see that this will produce naturally a thermometer code. So if the value is very small, everybody is 0. As the value exceeds this threshold, this will become 1. As it exceeds this threshold, both of these will become. And as it exceeds this threshold, all three will become 1. So you have 4 possible codes now: 0, 0, 0, 0, 0, and then 3 ones. Okay, one single 1, 2 ones, or 3 ones, or all zeros. Okay, so you have 4 possible codes, and you have to interpret this now. This output may not be convenient. Okay, so therefore now you need a thermometer code to binary converter here, which must be designed as a digital circuit. Notice that the delay of this will add to the conversion delay that you have. However, since everything happens in parallel, inclusive of this code, okay, so this is one of the fastest converters that you can have, right? So if I ask you to put your thinking caps on, and if I ask you what would be the equivalent of a flash D to A converter, integrator is a sequential process by nature. So what would be a flash D to A converter? Just to make life simple for you, think of a current rather than a voltage. So this R has a series switch. Okay, you've converted each reference voltage to a current by using R by 2 and so on, and added a switch, right? So if you just add up all these currents, right, then you will get the corresponding equivalent of flash D to A, right, in terms of current. Because the main mark of this is that everything must occur in parallel, right? Now notice I have sort of cheated you a little. I have taken an example in which there are only 2 bits. So it appears that it's not a big deal, but there are some very strong disadvantages associated with this A to D to A conversion. First of all, notice that the complexity of this doubles every time I add a bit. Okay, so rather than 4 levels, I need 8 levels, so I'll require 7 comparators. Okay, the 0, 0, 0 is when all comparators are flipped to 0, so I'll require 7 comparators. And in general, I'll require 2 to the power n minus 1 comparators. So while this scheme appears quite practical here, it didn't shock us when we saw only 3 comparators there. It can become quite shocking as soon, even if you reach say 8 bits. So if you want an 8-bit resolution, that means you require 255 identical comparators. This is one problem. The other problem is that the input, while you need a fast system, you are loading the input in parallel. Okay, the input sees all these comparators in parallel. So you are putting a huge capacitance on the input, and it is possible that the input driver, you may have a fast converter, but you can't charge the input to the value to be converted in the given amount of time. Okay, so this speed comes at a cost. Overall power is high, but also you can't go arbitrarily high in speed. Just by you may say that all right, 256 converters, so what? I'll produce any number of converters, any number of comparators that you want, but I want a very fast converter. But there is a limit to speed as well because of this loading aspect. Okay, your driver will have a finite output impedance, and R times 2 to the power n C, where C is the input capacitance of each comparator, will come across this. And as you add a bit, this capacitance actually doubles every time, becomes quite substantial. Therefore, you will start hitting a point where there is no point in trying to improve the accuracy of this. Therefore, it's obvious that this A to D, D to A kind of arrangement is convenient for a small number of bits. If you want, say, at the most up to 7, 8 bits, but much larger than that, it has too high a cost in terms of complexity and power, but also may become impractical just from the speed point of view, because you may just not be able to charge so many comparators in parallel. Okay, so sometimes then you have a kind of tapered buffer for these and take that hit in speed, but now you can perhaps charge so many. So you have a fact buffer which will drive 256 comparators, and then that fact buffer will be driven by another buffer, and that will be driven by the input. Okay, so you have a tapered buffer, but remember then the offset of all these buffers and so on will just add up. So therefore, it is really not practical for a conversion when you have a very large number of bits. That's quite obvious. So again, just so that you don't fall asleep, what would be the problem in D to A parallel D to A? Can that be made arbitrary number of bits? Why is there no power dissipation? Yeah, but essentially overall power is V by 2R. If everybody is on, so the current is V by R, V by 2R, V by 4R. So overall current cannot exceed 2V by R. Okay, so you choose your R property. That is not a fundamental problem. The problem is that the dynamic range of accurate resistors that you should have, okay, is too high. Right? So suppose you have, let's say 8 bit, then one of these resistors is R, okay, and the other resistor is R by 256. Now what is the absolute accuracy that you need in this R? If this R has an error of 1 in 256, then this error itself will swamp the current supplied by that much larger resistor. Right? So it is this thing which will limit now the corresponding D to A converter that you have. So that leads us to these conclusions. They are extremely fast, They are limited only in speed only by the time taken to charge the common inputs to the input voltage. That's the fundamental limitation, if you are not worried about power, complexity and so on. And the reaction time of the comparators, because the comparators cannot be infinitely fast. And the complexity essentially rises exponentially with resolution, and about 8 to 10 bits of resolution is the most that you can perhaps think about. Even that, 10 bits is 1000 comparators in parallel across the input is not an easy job to do. So beyond that, it's certainly not practical. On the other hand, they are about as fast as they can be. So then what is my next choice? That I suppose I need a higher resolution than 8 to 10 bits, and perhaps I don't care so much about speed. Okay. By the way, just to give you an idea, the conversion rates that you would expect in case of flash converters would be much in excess of say 100 megasamples per second. So it's only when you want conversion rates of that order that you would consider a flash, or I'm assuming that that is with a reasonable resolution, or the amount of resolution that you want is very small. In that case, that's okay. Okay, you could in fact even go to higher frequencies at that time. But generally it makes sense to go for flash converters only when you are talking of those speeds. So suppose you are happy with somewhat lower speed. By the way, that is not a limit. You can go to higher. But I'm just giving you an order of magnitude so that you have a gut feel of when we use a flash converter. So what is the next choice then? The choice is, if you can't have parallel, then eventually you must do it sequentially. Okay, bit by bit. If you want everything in parallel, then you have no choice but to have 256 times the complexity of whatever one bit will do, because everything happens in parallel, and for every step, therefore you need, where does this value fall, in which of the bins does this value fall, must be determined in parallel, and you have no choice but to have this kind of complexity, this kind of loading. If not, then what is my problem? Okay, so let us just look before we go to the details of the successive approximation ADC and so on. The problem is this, that I have some range and I'm trying to divide it. So I'm essentially asking a binary question. My value is somewhere in this range, and the first question that I ask is it in the upper half or the lower half? Right? That's the first question that I ask, just to refine it further and further. Now the point is that suppose it is in the lower half, then actually the problem is somewhat tractable. If it is in the lower half, then the next question I ask is that is it in the upper quarter or the lower quarter? Okay, but if it is in the upper half, I have two choices. If it is in the upper half, then I can now try to determine whether it is between half and 3/4 or between 3/4 and full. Okay, now if I do it in parallel and keep on doing it for larger and larger number of bits, I will end up with a flash converter, right? Because I wanted to answer this question and then answer this question. Then for each level, if I want to do it in parallel, I'll end up with a flash converter, because this question of whether it is higher or lower than this value is answered by a comparator, and therefore if I want to do it in parallel, so the question is, can I reuse my resources? Can I in fact say that this comparison for the upper range and this comparison for the lower range can be done by the same hardware? Okay, if I could translate the upper value to the value below, then this comparison and this comparison could be done by the same hardware. all I need to do is to subtract half the value or the value of the most significant bit. Right? This is one possibility. The other possibility is that I could raise my reference by half the value. So I had the reference at quarter here, the new value, new reference that I have introduced now is the quarter value. Right? So I could raise the value of the reference by half the bit and then do the comparison. Right? Both of them are okay. The only problem now is that I need to know the answer for the more significant bit. Only then I can go to the next bit. This part is clear? Because I am using the same hardware and action depends on whether the previous bit was 0 or 1. If the previous bit was 0, then I can do the comparison directly. But if the previous bit is 1, then I must translate either the input downwards or the reference upwards. Okay? And then the comparison will give me the same result and I can now do it at every subdivision. Okay? So this is the basic trick that I want to employ. Okay? So now the point is that my hardware will not go up in such a large ratio. Okay? Essentially the point is that if I agree to determine the answer bit by bit, then I can economize on my total hardware. Almost all the rest of the converters that we will see will follow that pattern in different ways. Okay? For example, a pipeline converter uses the same trick. This successive approximation uses the same trick. Right? The idea is to say that I will take of the order of n clock cycles. So that will take many comparisons. These comparisons will be done at different times but by the same hardware. Okay? So this is the common strand which will run in rest of the converters. So that is what I am trying to do. So essentially the idea is this, that I will not have fixed references. I will have a reference which is composed of a variable which is then coupled to a D2A. This is the basic idea, right? So I have now anyway, this doesn't need a diagram, otherwise I have to keep skipping back and forth, right? Quite simple. That now since I need a variable which can be shifted up or down, right? Your reference voltage needs to be shifted up or down depending on the previous bit. So rather than having a fixed reference, I am going to have a register and couple a D2A to that, right? And as I determine more and more bits, I will supply these bits to the D2A and shift my reference accordingly, right? So that's the basic idea in a successive approximation register ADC, right? So I have got this range and the next comparison will be done by the same hardware, and now I am shifting the reference, and the reference will be shifted depending on whether I found myself in the upper half or the lower half, right? So if I find myself in the lower half, then I don't need to shift the reference. The next reference can be V by 4, but otherwise I do have to shift it up, right? That is equivalent to saying that I have a larger number connected to a D2A where the most significant bit is already 1, right? So that is called a successive approximation register. You determine from most significant bit towards the least significant bit. Okay? Now you appreciate why the bits are numbered the way they are in A to D literature. Okay? We almost always have to go from most significant to least significant in time order. Okay? So that's why the lowest index number is often the most significant bit, because unless you determine the most significant bit, the methodology for the rest is not complete. You cannot proceed with the less significant bit. So that's why they are not just trying to be different for the sake of difference. It's not like date system between USA and India, whether month first or date first. It's actually functional, that you have to determine the more significant bit first, then go. So what are we going to do? You get a register. This register has the size of the conversion. This is called the successive approximation register. This register is trying to approximate the input. Okay? And then this drives a D2A converter. Okay? Now you compare the output of this D2A converter with the actual input. Okay, and initially you set only the most significant bit. Now the comparison will tell you whether it lies in the upper half or the lower half. Okay, now depending on whether you are in the upper half or lower half, you will leave the most significant bit set or clear. Because the next question that you want to ask is with the resolution of range by 4. Right? So you don't worry about the most significant bit. If it is set, leave it set. If it is not set, leave it clear. Right? That bit you have already determined. The next bit automatically represents an increment of 1/4 the range above what you have already set of this bit, and that is what you want to compare. Right? So therefore, next you will then try the next bit. No, so you first in the register you set the MSB. Okay, so MSB is set and everybody else cleared. That represents half the range. Okay, so now you compare it to the half the range, saying are you higher than this value or lower? Now suppose the input is higher, then you leave that set. Then if you now set the next bit, it will ask the proper question. If the most significant bit is 0, it will say are you in the quarter to half or half 0 to quarter or quarter to half range. But if this most significant bit is set, then it will ask are you from half to 3/4 or 3/4 to full. Right? So you just don't have to do anything. It is natural and automatic. Just leave the most significant bit set and now worry about the next bit. If the answer is that no, the input is actually lower than that bit, then you must reset this. Right? So that goes to the obvious methodology. So it's made from a register, an SAR, which drives a D2A converter. You can make conversions 1 bit at a time. That's the only way you can do. Go from most significant to less significant bits. And the current bit which is being evaluated, in the first case the most significant bit as we had said, is unconditionally set to 1. And then you find whether the input is higher than this or lower than this. Okay? If the input is indeed higher, then you leave it at 1. If it is lower, you clear it and then ask for the next step of resolution and so on. Okay? So this part is quite natural to do. Essentially, you are just changing the resolution every step. So how many steps will you require now for n-bit conversion? At least n clock cycle. You may require then 1 bit to then register this output or whatever. But typically of the order of n clock cycles will be required. Now that is not too bad actually. Speed wise, it is quite slow. Maybe an order of magnitude slow if it is 10 bits compared to a flash converter. But the flash converters are so fast that even though I am as much as an order of magnitude below the flash converter speed, these are useful speeds for many applications. Okay, it turns out that this is actually a pretty good bargain, and successive approximation register converters are used very frequently in practice. They are the answer to many requirements, perhaps the most widely used architecture for A to D, unless there are special requirements, perhaps the most widely used structure. Okay, so what are the characteristics? They are fairly fast, about an order of magnitude slower than flash, fairly fast. But now the complexity increases only linearly. Okay, so that means the register has to be 1 bit higher and the DAC has to be a bit higher. Okay, I am assuming that I have not quietly swept the complexity into the DAC. Okay, we did say that DAC will become complex, and we are assuming that the DAC responds immediately. Right? So that we have to go back and examine that carefully. In fact, it is that which will set the highest rate at which you can clock it. N clock cycles are required, but what is the period of this clock? That will be decided by the rate at which your DAC settles and your comparator produces an answer, right? So these two together will represent what is the period of the clock. The number of clocks will be decided by the resolution that you want, but the period of the clock, after all it is n times t, that is the time taken for the conversion. The period of the clock will now be decided by how much time does the DAC take and how much time does the comparator take. Inaccuracies of DAC will reflect in your output. So eventually that will represent the final limit on your this thing. It turns out in practice that the speed is limited by the comparator, because there are various tricks that you can use. The D2A, remember, it's monotonic. The value on the output of D2A is increasing monotonically. It does decrease sometimes, but the point is that the bits are always being set. You may reset the previous bit, but then the bit is being set, and because of that the value doesn't change that dramatically. So you are not that much slew rate limited. That can become a problem, but you are not that much slew rate limited. On the other hand, the output of the comparator has to go from rail to rail. It has to slew the entire power supply range from 0 to VDD, whereas the reference is going in steps, small steps. So in terms of sheer slew rate, the limitation will come from the comparator as far as the speed is concerned. On the other hand, the accuracy is limited by both. So you need a very good comparator and you need a pretty good D2A. Now notice that while all of this going on, you are assuming that the input is steady. Suppose the input changed in between, then it can confuse the hell out of your A to D converter, right? Because initially you said the MSB is higher, and by the time you go to the next bit, the MSB was lower. You may get totally wonky results. Okay, may never converge. So therefore, it is important that the input be held dead steady while this conversion is going on, and therefore you require a class of circuits which are called sample and hold circuits. They copy the input and hold it steady. Okay, they are the analog equivalent of a D flip-flop. So they take a snapshot of the value and hold the output steady at this value till the conversion is over. So the actual input may change, but the value which is being converted is held at this value. So you need a circuit which is called sample and hold, the equivalent of a D flip-flop. The value is taken and then the output is held steady at that value. The input may change afterwards. Okay, we are not looking at implementations today. Next class we will see how to implement these, but today we want to understand how these converters will actually work. Now there are another class of converters. These are called charge balance converters. Okay, so essentially these are analog to time conversions. So what you say is that I will deposit a packet of charge on a capacitor, so it will keep on building, and when it exceeds the input, then I'll stop it and I'll count the number of clock cycles it took me to reach the input. Okay, again these will require a sample and hold, right? And these are sometimes referred to as single slope conversion. Okay, because what you are doing is that you are starting out with some slope which depends on how much charge you are putting on this capacitor. So every time step you are putting a little more charge, linearly increasing the value. Okay, notice that these will be quite slow. For n bit you will require up to 2 to the power n steps. Okay, then you balance the total charge on the two. There are various schemes for this charge balancing. Notice a slight subtlety of terminology: charge balance versus charge sharing. Okay, charge sharing converters could include, for example, successive approximation registers and so on. Okay, those are faster. Now, right now, what I am talking of are essentially you have an integrator, right? So you take this integrator. This integrator is discrete, as you have done switch capacitor. So by switching capacitors, you can make it discrete. But otherwise, it is just an integrator. You are holding your breath till the comparator trips, and when the comparator trips, you just look at the value of the counter and say it took this long to equal the input, and therefore the input must have been higher or lower. So that's the trick that you are using. One advantage of one big advantage of charge balancing ADCs is that it is very easy to make them monotonic. That means if the reported count is higher, it guarantees that the input voltage would have been higher. Okay, now you might say that should happen with every A to D. If the input is higher, obviously the A to D output should be higher. But the binary weighted cases, what happens is that if there are inaccuracies, and if you switch the binary from most significant bit from 1 to 0, then the inaccuracy in that could be more than the least significant bit. Okay, so it is possible that 100 actually is smaller than 011, right? The corresponding analog quantity, if the inaccuracy in the most significant bit is. So those are very bad A to D converters, by the way, but those are non-monotonic. Now, monotonicity will hardly ever be broken at the most significant bit, but this applies all the way down, and therefore the inaccuracies when the bit values become quite small are difficult to control, and therefore you cannot give a unique guarantee that this will be monotonic. Okay, that the value to count will always be monotonic. It may be inaccurate, but you say that if my count at the output is higher, then the input must have been higher. Okay, by how much? Let's say we are not worried about, but the monotonicity has to be asserted, and this is required, by the way, in many, for example, in control circuit, which say which way should I change the impedance. Okay, so it worries if you change the impedance in the wrong direction, your control algorithms may go completely haywire. Okay, also lots of nuclear instrumentation and so on. It is the monotonicity and linearity is very, very important. Okay, so since you are putting the same packet of charge on the capacitor at every clock, it is possible to get very high values of linearity and monotonicity. The input, since the same packet of charge is being put every time, if you can ensure that, then the input will rise quite linearly with every count, and therefore the linearity can be made quite high, and also monotonicity, because if it took longer to balance the input must have been higher. There is no other way that you will make a mistake there. So therefore those applications very often use charge balancing. However, the disadvantage is that the conversion is very slow. Every bit that you want to add, the number of clock cycles doubles. Okay, so this is essentially doing to you in time what the flash converter did to you in complexity, right? So the times may become unacceptably high once you want very high resolution. Sometimes the requirement for linearity and monotonicity is so high that you still take that hit, and there is a fair amount of nuclear instrumentation which takes this hit. They will take sample and hold and do a slow conversion, but they absolutely want this linearity and monotonicity. The reason for that is that they want a differential. They want a differential of two values. Whenever you have something which is sensitive to the differential of the two values, then linearity and monotonicity become very, very important. If it is not monotonic, then it will change sign from the true value when you take the differential. So anything which is sensitive to the differential, and many nuclear things depend on the rate of change of the energy with whatever control variable. So therefore those are the ones which use this kind of converter. Now let's see charge redistribution, and I think it is a strong jump, but we will work it out rather slowly. Okay, because this thing actually combines, by the way, all successive approximation register architectures then combine D2A with A to D. This is one of the reasons that I have not made such a big distinction between D2A and A to D. So then when you are constructing an A to D, you must also construct a corresponding D2A. Okay, so one of the ways of doing this is to do it with binary weighted capacitors. Okay, so let's look at this particular technique. There is one other trick here which is somewhat important, and notice that this output, okay, is there with a capacitor. Even though the output is DC, you have a capacitor there. Okay, now this needs to be worked on. So what we will do is that before we go to the details of this, of how this works, let's understand what we are doing here. What is this capacitor there for? In fact, there is a switch here and a capacitor here, which is quite important. So let's look at that first, then we'll come back to this charge redistribution. We have the time. Okay, so let's look at this. Eventually, your accuracy is going to depend on your comparator. Right? Suppose the comparator has an offset, then the least bit that you can resolve cannot be larger than this offset. Therefore, offset is very, very important. Removal of offset is quite important. Now, practical comparators will eventually have some offset. So now we need tricks which will allow us to remove that offset. Okay, and one of these tricks is that if I can have a system which measures its own offset and subtracts it out, then I can have a larger accuracy, right? A better. So I will pretend as if I have got a very good comparator without any offset, and I will pay in time whatever it takes to measure and to subtract this offset. That is the basic trick that I am going to talk about. So how do I measure the offset? Suppose you have an op amp, okay, so think of the comparator right now as if it is an op amp. How do I measure the offset? Measure the output. That will measure the offset at the, in a closed loop. So where are you closing the loop? So you put it in a unity gain configuration and short both the inputs, and now measure the output. And what will that measure? It will measure the input output, right? So what is being suggested is this, that this is my ideal op amp. My real op amp has an offset. Okay, so I model this as if I have an ideal op amp and I have a battery which is not accessible to me. And my real op amp is essentially this op amp. Okay, I am by the way using the terminology op amp, it applies to comparators. Right? So this dotted line op amp is my real op amp, and it is in other aspects the same as an ideal op amp, but it has got an offset. Okay, now the behavior of this dotted line op amp will be that of an ideal op amp, but which has an offset. Right? The idea is how to remove this voltage, how to measure and to remove this voltage. Right? So one thing as is suggested here is that I configure it in a closed loop formation. Okay, and short the input. The input voltage is, input differential voltage is 0, right? So if I short this input, what will my output be? Suppose this is the offset. So you can think of it as this. Right, the shorting is from the other end of the battery, right? Negative end of the battery. right? It's the same circuit that I have drawn here. Right? So essentially the output is equal to this unity gain, ideal op amp, unity gain, and the output voltage is the voltage of this offset battery. Right? You got that? Essentially it is the actual op amp is offset, its gain is 1. So if it is offset by some voltage, when the input is 0, the output will be the offset voltage. Not a big deal. Right? Yeah, so right now I am talking about differential voltages. The reference could be anything, then the output is also measured with respect to that. Okay? So there is a differential offset voltage which is there between these two. So if I measure with respect to the same reference to which the input is applied, then the output voltage is a measure of the offset of this. Okay? This can be stored on a capacitor now. Right? And this voltage then with some switching mechanism, which we don't know right now, but with some switching mechanism can be subtracted from the input every time because of this offset. Yeah, you can still, but in many configurations you may not have that freedom. Okay, if both inputs need to be, essentially what it matters is that the output is a measure of the differential voltage. Okay, so when the actual differential voltage is 0, it reports a VOS at the output. Okay. Still, yeah. So in fact, that is the next thing. When I compare the offset correction at input and output, that thing will come. So right now, we have assumed that the unity gain is ideal. But eventually my real op amp will not have infinite gain. So what I will store here is in fact approximating the offset voltage, but it is not quite the output voltage. Okay, this is one possibility, right? Roughly this is what has been suggested for the offset correction. This is called input offset correction. So this stored voltage must then be subtracted from the input which is coming. The other correction is called output offset correction. Okay, and that's why I had drawn that strange configuration of floating, because we want to compare it with this. Now this is our imperfect op amp. And all I am going to do is, I am just going to short the input. Notice no feedback. Okay, so it is actually in a configuration where the gain is finite. Okay, this is a non-ideal op amp and it might be the input stage of an op amp and maybe it has some feedback etc. which I am not fiddling with. So overall gain in this configuration is finite. Okay. So as a result, when I give it 0 input, its output is non-zero. And how much is the output? Offset times the gain. Right? When we define the offset at the input, offset times the gain appears at the output. So this capacitor then gets charged to the output offset voltage. Okay, so now I can do a trick. I can move this switch from the upper end of the capacitor to the lower end of the capacitor. Okay, so this is what I do. Now, suppose I short the input and ground the output. Right? It's the same configuration as before. Then the gain times the offset that will stored on this capacitor. Right? Suppose next I put the actual value here. Okay, so let's say that the gain of this is G, right? So when I applied 0 input value, what was the output value? G times V offset. This is where this output was resting initially, right? When I shorted the input, the output was resting at G times V offset. Okay. Now suppose I connect the V input. What is the input that is seen by the comparator? It is V in plus V offset, right? And that whole thing is multiplied by G, right? So in the active cycle, the output is what? G times V in plus V offset. Right? I am not shorting the input anymore. So since there is this internal battery in series, so when I apply some input, this battery will come in series with that, and therefore the actual voltage seen by the imperfect op amp is the input voltage applied to it plus its offset, right? And that whole thing will be multiplied by its gain G. Okay, now what happens? So what is the change in the output voltage? G times V in. And therefore if I put this capacitor, initially this was at 0, and when I switch it, it will show the change, right? So the output will now be G times V in. This part is clear? Right? This end of the thing has gone from G times V offset to G times V in plus V offset. Therefore, this will go from 0 to the amount of change which is here, you will get the same amount of change here, right? So it will go from 0 to the change, and the change has the offset cancelled. V in is, no, I am assuming that this capacitor is large enough to pass that frequency. Okay, so capacitor is selected to pass whatever is the input frequency. But the idea is that they offset. In fact, in A to D conversion, very often we are talking of quasi DC. Okay, of course, time of conversion is important. So this capacitor should charge up to this difference within the time that you have given in case of A to D conversion. Okay, now we have two ways of correcting this offset. One is at the input, which you saw before. The other is at the output. Now, what are the pros and cons of using both of these? Okay, and then we will choose one of these. By the way, this is the series capacitor with a switch and a shorting switch at the input. That is what you saw in the diagram. Okay, and that charge redistribution A to D converter is ideal for that configuration because you don't have to pay anything. Those things are anyway there. Okay, so you don't lose any time in using this conversion, but that we will come to. No, so we are coming to that. So then, what is the comparison between the input offset correction and the output offset correction? One problem with the output offset correction could be that this initial voltage itself could be so high that you are not in the linear range at all. Your op amp is saturated, right? In particular, it could certainly be saturated here. That means G times V in is not sufficient to saturate the op amp, but G times V in plus V offset is sufficient to saturate the op amp. Okay, then we'll have problems, right? So therefore, we need to make sure that this doesn't happen, because we are assuming that everything is linear. Take the difference, it will correct the offset. That is true if the gain remains the same. That means you have a linear system, right? The gain remains linear over this range. So therefore, this will not work if you don't have sufficient headroom at the output of your op, right? And that requires that the product of G times offset should be reasonably small. And therefore, you must be operating this at a low gain. Okay? Therefore, to make use of this, you very often split the comparator in several stages. And the first stage is a relatively low gain stage, which you correct using output offset correction because the gain is low. And because of that gain, if this guy has zero offset, then the offset is input referred offset can now be reduced by other high gain stages, which will follow this. So overall, you can still have high gain stages, but a part of that gain has already built up your signal compared to the offset without adding any offset. Okay, so to give you an example, let's say that I had a gain of 4, and let's say that you have an offset of 1 millivolt and a signal of 1 millivolt. Now this is too bad. So if you didn't do anything, and you, let's say you want a gain of 4,000 overall. So if you didn't do anything, then your input will be swamped by this offset, right? But what I'm saying is that you take a gain of 4 first with offset removal. So then signal plus offset is small enough, you can do this with a gain of 4. Now what happens? Your signal has become 4 millivolts and the offset is only 1 millivolt. Now if you amplify, your signal to noise ratio has improved quite a bit, right? So it will be improved by the gain of the first stage. So that decides how much gain you will have, because how much signal to noise, signal to offset improvement you want. If you want more, then you need high gain. But then at the same time, you have to make sure that G times V offset doesn't become so large that your output gets into the nonlinear range. Okay? So this is the trade-off that you must have in the first stage of a multi-stage comparator. But why bother? Why correct it at the offset? Output, excuse me. You could, after all, we saw that we could correct it at the input. And if you correct it at the input, then there is no question of going into saturation, right? You have already adjusted the input so that a large input is not presented to this op amp. Then whatever the gain, you will be okay, right? Yeah, so you need a gain of 1. But in reality, the gain is not 1, right? So the gain is actually A upon 1 plus A, right? You have 100% feedback, beta is 1. So the gain is not quite 1, it's A upon 1 plus A, right? So therefore, what is the gain error? How different is it from 1? Roughly by 1 by A, right? So your gain error is 1 by A. That means what you stored will not be quite V offset, but it will be V offset into 1 minus 1 by A. The gain is slightly less than 1. Okay, it is smaller by 1 by A. Okay, just a binomial expansion of this to first order. Okay, so 1 plus A raised to power minus 1 into A. So that will give you that the gain is not quite 1, but it is this. So what is the residual? We want this V offset. That should be subtracted. But rather than subtracting V offset, you ended up subtracting V offset times 1 minus 1 by A. Right? So therefore there is a residual of the V offset left. What is that residual? V offset by A. But that will further be amplified by A. Right? So essentially in this case, the input offset will become the output. Okay? It is, you still gained a lot. It would have become G times input offset. But the input offset is not fully cancelled. Okay? It will in fact appear at the output. Some residual will be there rather than being 0, even in the ideal case, if the gain is finite. Okay? So that is a problem with the input offset correction. And this is a problem if gain is low. If the gain is high, this is small. So that tells you that if you want high gain, if you have high gain, use input offset correction. If you have low gain, you can use output offset correction. That will be better, right? But there is one other major, from this you would have said, what's all this? Eventually we want high gain. Why are we even discussing the output offset correction? There is one major difference between a comparator designed for input offset correction and a comparator designed for output offset correction. And what is that difference? If you have a feedback for unity gain configuration, then this op-amp needs to be compensated. Right? Have you all done in the other analog course op-amps? You have gone to a compensation. So you know that if there is feedback, you need compensation. Okay? Now this is a large capacitor and it reduces the bandwidth of your op-amp. Right? You put a Miller capacitor there, it reduces, so it makes your op-amp relatively slow. Now if you are going to do input offset correction, then you are going to put it for a short time in that unity feedback consideration. And you know that the unity feedback consideration is the worst case for stability. Right? The entire output is being fed back. That is the worst case for stability. Therefore, you require full compensation for this comparator now. Now that's a pity, because while it is in operation, you don't have feedback as a comparator. And therefore, you could have avoided that capacitor and you could have had a much faster comparator. But just because you want to do input compensation, you are now required not only all the complicated switching arrangement which will store and subtract the value, but apart from that, now you need to have a fully compensated op-amp which is much slower than what it could have been. Okay? So these are the trade-offs between input offset and output offset correction. If you want the fastest possible comparator, then you would perhaps settle for a multi-stage comparator in which the input stage, first stage, is just sufficient to suppress the offset voltage. Okay, so you would have a low gain first stage with output offset compensation and the rest with high gain using multiple stages. Right? So generally you would split the gain into several stages and optimize so that the overall delay is minimized. Okay, that would give you the fastest compensation. Because generally this capacitor is so large, you have seen most of the designs and so on, that it does cut the bandwidth by a huge amount. So it cuts the gain anyway at particularly high frequencies. Okay, so you have to do a very careful design for that. No. The correction is being done at a different time. Then the correction is removed. So that configuration of unity gain is only while measuring the offset. Then you will remove that feedback during the actual use. Yeah. The comparator is essentially a high gain op-amp, right? High gain amplifier. It takes one LSB or half LSB and amplifies it to a full rail-to-rail swing at the output, so that the output will be 1 or 0. So you can think of it as a very high gain amplifier. Okay, but the luxury of not having feedback is that you can have an uncompensated op-amp and get the best performance at this technology. Okay, on the other hand, if you use feedback, then you are forced to put a kind of compensation which actually kills the gain as well as the bandwidth of your amplifier. So other stages can also be, now you have a choice whether how much speed you want. So you could have medium gain and input offset compensated, but remember that then those will require the compensation. So anything which is input offset compensated will require the Miller capacitor or whatever you are using for stabilization of the op. If you are using only output offset compensation, then your range is quite limited over which you can correct. Okay, but if you can be within that range, then you don't worry about it. Okay, and the other thing that we will see today, we don't have the time, but we will pick up the thread in our next class, that in the successive approximation case, this comes for free. Because in the first stage, you are anyway supposed to short the input to 0. Okay, you begin the whole thing by shorting the input to 0. So during that time, when you are shorting the input to 0, you don't lose any time. You can just look at the output and store the output on a capacitor and subtract it from all the subsequent outputs. Okay, so you don't pay anything in time. You just need to add a few capacitors. Therefore, it is quite advantageous to have this sort of compensation in successive approximation registers, particularly in their first stages. But that detail we will see the next time. Alright, just a quick review of what we have discussed today. First of all, we have introduced this topic of A to D. Remember that half bit offset in terms of A to D versus D to A. Right now, we will never consider it. It doesn't matter. But when you have feedback systems, then that matters. Okay. The other thing is that we have looked at the representation systems of various ways of representing the digital world from that. We have looked at various architectures of this, and we have looked at the basic problem of sequential conversion. That means the MSB must already be known if you are doing sequential before comparing the input, and therefore things are necessarily in sequence one after the other, and that makes things slow. So if you cannot take that hit in speed, then the only way to go is to go in parallel, and that requires huge complexity, right? Next time we will see that in fact this speed must be resolved to two separate things. One is the absolute delay or the latency, but if you don't want particularly short latency, you only want high throughput, then there are other tricks that we can use and still have reasonably fast A to D conversion without paying the price of so much complexity. Okay, we will see that these things next few classes. Okay, stop here. If there are questions that I didn't cover at the proper speed and so on, we can discuss that now. Okay, most of this actually would have been repetition, because I'm sure somewhere or the other you have done A to D conversion, D to A conversion at this detail itself. But we will go like this, and then we will take actual implementations.